Module 5 is on exponential and logarithmic functions. We will discuss definitions and examples, graphs of the different types of exponential and logarithmic functions, how to solve exponential and log equations, as well as several growth, decay, and various other exponential and logarithmic application models. Let's start with exponential functions. Exponential functions are functions of the form y equals a to power x, where a here is a positive integer or positive number, really more generally. Let's start by taking one example of an exponential function and sketching it. So before we proceed to sketch, first of all, notice that this function is just 2 to the x, but this other function, 2 to the negative x, can be rewritten in a number of ways. So recalling the exponential laws, and if you can't, please take a look at module 1. This is the same as 1 over 2 to power x, or it's also the same as 1/2 all to power x. So if I were to sketch the graphs of 2 to the x and 2 to the negative x on the same set of axes, what I would like to do is start by constructing a table of values. So I'm going to have values that I choose for x, values for the y coordinates of the function 2 to power x, and also values for the y coordinates of the function 2 to the negative x, or again written in one of these alternative forms, whichever way you prefer to calculate it. When you choose values of x for the table of values, please make sure that you choose from a variety of numbers. In particular, do not forget that negative numbers are also a part of the x-axis, so this is also some of the values where you would like to evaluate the function. So let me maybe plug in 0, 1, 2, -1, and -2 for a variety. And if you ever think that this is not enough, you can plug in more numbers to see a bigger pattern emerge. So 0 plugged in into x, 2 to power 0 is 1, 2 to power 1 is 2, 2 squared is 4, and we recognize, of course, that if we increase these numbers further in this fashion, the y values for this will also increase. And now we come across a negative value. So I'm plugging in -1 into the power here. 2 to the -1 is 1/2. For the next one, 2 to the -2 is 1/4. Okay, so here we also notice that the more numbers in the power go into the negative side, the smaller these fractions will become. So if I were to sketch what I have already, I noticed that when x is 0, the y-intercept is 1, and then I can note that these are the points that I'm interested in. So at 1 I have a 2, at 2 I'll have a 4, and the function will grow quite quickly in this direction, whereas if I plug in negative values, as I've noticed, the fractions will get smaller and smaller, so I will be getting closer and closer to the x-axis for negative values of x. Notice though that no matter how big a negative number I plug in, because of the relationship, because of what it means to raise something to the negative power, the outcome here will actually never be negative. It will be 1 over a large value, so it will get closer and closer to 0, but never quite equal to 0, and will never drop below the x-axis. For the second graph of 2 to the -x here, let's plug in the corresponding numbers. Maybe let me do it in different colors so that it's a little more visible on the graph. 2 to the power of 0 is still 1, 0 and -0 is the same. But now when I'm plugging in a positive value of 1 here, I'm going to get 2 to the -1, which is 1/2, 2 to the -2, which is 1/4. So as the numbers in the power increase, the fractions decrease. And so if I put these points on the graph, I'm going to once again get the same x-intercept, but then here I'm going to get smaller and smaller fractions. And then of course I notice that if that keeps going, I'm going to again approach the x-axis infinitely closely, but never quite touch it and never cross it. On the other hand, if I plug in negative numbers into the x here, I'm going to get 2 to power -1, or 2 to power 1, so 2. And same for other negative numbers. 2 to power negative negative 2 is going to be 2 squared or 4 and so on. So as the numbers here increase into the negative, the values for y will grow larger and larger. So for negative 1 I have 2, for negative 2 I'm going to have a 4, and in fact I noticed that this graph will essentially mimic the other graph, but will be a reflection of it in the y-axis. Okay, this is going to be the general shapes of the exponential functions, where you have the base that's bigger than 1 and the graph will represent growth, and where you have the base less than 1, or the other way to think about it is if you have a negative power, where the graph will represent exponential decay. Now, these are just the graphs with the base of 2, so this number we call the base. Let's take a look at what happens when we change up the bases a little. So here I have a variety of different things to sketch, and we should sketch them all on the same graph just to see how all of these graphs interact with each other. I strongly encourage you to take a minute here and actually construct a table of values for these different graphs to ensure that you understand how we come up with detailed and precise sketches of them. So first of all, let me start with, let's say, 3 to the x. If x is 0, my graph is going to have a 1 as the intercept because 3 to power 0 is 1. Then if I plug in x equals 1, I'm going to have a 3. And if I plug in 2 and so on, my graph is going to grow. Whereas if I plug in negative values, I'm going to first have a third and then a ninth, and so my graph is going to decrease. And so I get the shape that is similar to that of 2 to the x, except for 2 to the x would have lied for 1, it would have been 2, for 2 would have been 4, so the 2 to the x graph would have looked slightly different. Similar shape, but slightly different. If on the same graph I am now to sketch 5 to the x, I once again notice that 5 to power 0 is still 1, so I'm still going to have this point right here. But now at 1, I'm going to have a 5, so my graph will surpass that of 3 to the x immediately after the y-intercept here. But on the negative side, I'm going to have 5 to power negative 1 is minus 1/5, which is below minus a third. So on the negative side, my graph will lie below the 3 to the x graph. Okay, so at the y-intercept is where the switch happens. First, the 3 to the x was dominating or on top here, and then after the switch, 5 to the x actually surpasses it. The graph of 4 to the negative x, let's just work with it for a second. Negative power means positive power on the bottom, which you can also then, using exponential laws, turn into a quarter to power x. So that means that this graph will be similar to that of the graph of 2 to the negative x here. So at minus 1, it's actually going to be 4. It's still going to go through the y-intercept here, but it's going to be an exponential decay graph, so facing in the opposite direction. Okay, so notice that, for example, if I was sketching 4 to the x, it would lie right between 3 to the x and 5 to the x. The higher the base as an integer, the steeper the graph is, and it will do so in order. The next graph is minus 4 to power x. So notice here that this minus is actually outside of my exponential function. It's important to remember that in the exponential function definition, the number a, which represents the base, has to be positive. So here, it will be probably better if I put the brackets around 4 to the x, just to emphasize the fact that it is not minus 4 that is raised to power x. Rather, it's 4 raised to power x that has been negated. Okay, now that just means that I'm looking at the graph of 4 to power x, and then I am reflecting it in the x-axis. So it's actually going to be a graph that looks something like this, probably a little steeper on this side to make sure that it's somewhat consistent, because its counterpart on the right side would have to lie between 3 to the x, and 5 to the x. So this is minus 4 to power x. Okay, so be careful about where the minuses occur and how they affect the graph. The last graph we're asked to sketch here is e to power x. Recall that e is simply a constant. It is one of the most useful mathematical constants. It is approximately equal to 2.718. It does not have repeated decimals, so it's a number that never actually gets a pattern to it. But it is approximately, we can think about it as 2.7. So it lies somewhere between 2 and 3, sort of closer to 3. So if I were to sketch a graph of that function, which is going to be one of the functions that we use in applications all the time, it will have to be between the graph of 2 to the x and 3 to the x, but of the same shape. So if I am to do it on this sketch, it's going to be above all graphs here. It will still go through the same y-intercept as everything else, and then because it's slightly less than 3 to the x, it will lie below the graph of 3 to the x here. So this graph is that of e to the x. E is what we call when we talk about logarithms, we will talk about a natural exponent. This is the same e as occurs here. So again, this is just a constant that occurs in nature. It occurs very naturally in mathematics, and in calculus you will actually see what is so special about this particular base as opposed to all the other bases, and that has to do with tangent lines at this particular point. Keeping all of this in mind that we've just discovered, let's list some of the properties of exponential functions that we have noticed. So again, recall that exponential functions here, I am talking about y equals a to power x, where the base a is positive. Sometimes the books will describe exponential functions as having constants in front of them as well, and constants in front of the power. We're going to talk about the most basic exponential function. So one of the things that we've noticed is that the functions that we have drawn all have y-intercept of 1, and that is of course true because a to power 0 is equal to 1 for any a, which means for these exponential functions 1 is always a y-intercept, or the y-intercept, because it's a function, so there can only be at most 1. The other thing that we can talk about, of course, here is the domain and range. So what are the possible x values and what are the possible y values? For the domain, we notice that we can plug in any number for x and it will give us a real number as the outcome. So the domain is all real numbers. But for range, again, talking about just the basic exponential function, we noticed right in the very beginning that no matter what x's I plug in, the values that we get out will always be positive. I will never be able, as a power, to get a negative number or even a 0, which means that the range will be all y's that are strictly greater than 0. Even 0 is not attainable. Now, this in itself means that a to power x is positive, strictly positive, for all values of x. Okay, and this will come in very handy. This property will be very useful when it comes to solving equations that involve exponential functions, and in particular for calculus things such as finding critical points and whatnot. We also notice that as we get closer, as the numbers, for example, here become more and more, as the powers become more and more negative, we get closer and closer to the x-axis. So the x-axis is a horizontal asymptote for the exponential function. And notice that it doesn't matter whether the exponential function was the one that was increasing or the one that was decreasing. For the increasing ones, the x-axis was the horizontal asymptote on the negative side, and for the decreasing functions, it was the horizontal asymptote on the positive side. And that is another property that we can state here, is that we notice that if we have in the base the numbers that are bigger than 1, then the general shape of the function is increasing. Whereas if we had in the base numbers that are less than 1, the negative exponent representing a fraction as the base, then the graph was actually decreasing in nature. Okay, so this is something else that we can list in properties here. A to power x is increasing if a is bigger than 1, and a to power x is decreasing if a is less than 1. Notice that I'm not including the case of 1 because 1 to power x is just 1 for any x, so that will be the graph of a horizontal line. Transformations can be applied to any function. So now that we know how to graph 2 to power x, we can graph graphs or functions that are based on that. So recall that the transformations that are applied directly to the x here, so this 3 will mean a horizontal shift. In this case, plus 3 means 3 units to the left, and this negative 5 here will mean a vertical shift of 5 units down. So I can start by sketching the basic graph of 2 to power x and then performing the necessary transformations to get the graph of a function that I want. So recall that 2 to power x will have the y-intercept of 1 because 2 to power 0 is 1, and it's an exponential growth function, so it looks something like this. This is 2 to power x. For the graph that we have to sketch, we have to transfer this entire picture 3 units to the left and 5 units down. Now, it's easiest, I find, to grab a point that you know something about and then move that point before you move the entire structure. So this point of 1 has to move 3 units to the left and 5 units down. 1, 2, 3, 4, 5. So this point now will represent the exact equivalent of this point 1 here, and we can of course list its coordinates, -4, and here -3. Now the x-axis was the horizontal asymptote for my original exponential function, which now means that x-axis shifted 5 units down will represent a horizontal asymptote for my new transformed function. Okay, so keeping this in mind, I can now of course create a fairly reasonable sketch of my function. It has to have this line as the asymptote, has to go through this point as it would have had a y-intercept, and then continue exponential growth. In order to make my sketch a little bit more precise, I can try to find other points. So for example, I can see clearly here that my graph, no matter how I draw it, will have to intersect the x-axis and the y-axis. The y-intercepts are usually fairly straightforward to find, so let's look for that one. Y-intercept of my function, it is when I set x to be 0, and we compute the corresponding y value, so this will be 2 to power 3 minus 5, or altogether 3. So I know that my new graph will intersect the y-axis at 3, and this alone should give me enough flexibility to sketch a fairly, or rather enough structure to sketch a fairly reasonable graph of my function. So this is my function f of x. The question also asks about its domain and the range, so let's think about those. Domain are all the possible x values. Clearly here, I have not introduced denominators or square roots. I can still plug in any value of x, so the domain remains to be all real numbers. The range, however, has changed a little, or rather quite a bit, right? So the range used to be, for this function, for 2 to the x, everything above 0, but now the whole picture has been shifted down. So I can see that I can never get anything below -5, but I will get everything above it. So the range will be y values, all of the y values that are strictly greater than -5. The other piece of information that would be nice to have about this function is this x-intercept, right? So let's try to find out how we will solve for the x-intercept. We set y to be 0 and then solve for x. So I would have to solve the equation 2 to power x plus 3 minus 5 is equal to 0. I can try to isolate x, and I will get 2 to power x plus 3 is equal to 5. But then I don't yet have the tool to bring the x from the power somehow down to the place where I can really solve for it. So this is something that we still have not developed tools for. So let's spend a little bit of time thinking, how can one approach solving equations like these? We will first think in terms of just bare bones and dealing with exponential functions before we really develop the theory of inverse functions and logarithmic transformations. So let's take a look at some easy examples first. Let's call them easy. The first one, 2 to power x equals 8 squared. So the one thing that we can try to do is get both sides of the equation to have the same base. So in this case, I can see that 8 is 2 cubed, so I can replace 8 with 2 cubed, and then the whole thing was squared. I can simplify this expression on the right by remembering the exponential laws, that when I raise a power to a power, I multiply them, so I have 2 to power 6. And now that I have the exact same bases, if the bases are equal, the exponents also have to be equal, which immediately gives me x equals 6. So this is great, but now this only really works if I have bases that can be somehow reduced to the same number, which was not really the case here. I cannot write 5 as 2 to the power of something nice, like an integer. Let's take another look at a similar example coming up next, just to be sure that we understand that sometimes, even though things don't look like they can be reduced to the same base, they actually can. So here I have 1/2 and 8, and I will reduce them both to the powers that have 2 as a base. So 1/2 is actually 2 to the -1, and 8 is actually 2 cubed. So I'm going to replace those numbers with those representations in base 2. So 2 cubed and all raised to the power of x plus 1. And now I have 2 raised to a power to a power. So again, using exponential laws like we did here, the powers get multiplied in. So I'm going to get 2 to power minus x plus 4 equals 2 to power 3x plus 1. And the same logic as before. If the bases are the same, then the exponents have to equal. Will give me minus x plus 4. Don't forget the bracket here, or you will lose a negative, equals 3 times x plus 1. Now the good news, of course, is that this is just a linear equation. The highest power of x that I see is 1, so we can just open up brackets, isolate, and solve for x, which will give us x equals -7/4. If you have any issues with following exponential rules or with solving linear equations, then please take a look at earlier modules where we discuss this and have lots more examples to practice with. Let's take a look at this equation now. So what we have here is a mixture of powers of x and exponential functions. What I can see though is that I have the exponential function present in both terms, and so I can factor this guy out. So taking out e to power x, what we have left is x squared minus 2x, and this whole thing has to, of course, be still equal to 0. The power in factoring is in the fact that a product of two things or more than two things is only ever 0 if one of the factors is 0. So this immediately gives us that either e to the x is 0 or x squared minus 2x is 0. Now this I can actually factor out even further. So I'm going to have x minus 2 is 0, which means that either x is 0 or x is equal to 2. So these are my two possible solutions, and I still have to actually solve this portion of the equation. Now remember that e is just a number. It's like 2.718 and whatnot. So I am raising a number to some power. Raising a number to any power will always produce a positive result. We will never be able to get 0 or anything below 0. This was one of the properties of exponential functions that we came up with on the previous page. So that means that this portion of the equation produces no solution. So our only solutions here are going to be 0 and 2. Great. Moving right along, let's take a look at this equation. This one looks quite a bit more complicated, but it has a familiar structure to it. So notice that I have e to the x and then I have e to the 2x. I can rewrite e to the 2x as e to the x all squared. because again, remember, raising a power to a power means multiplying the two together. So then I have e to the x squared minus 5 times e to the x, and I will introduce the brackets here just to highlight the structure that I'm seeing. And then what you actually have is something squared minus 5 times that same something plus 6. So look at this equation, maybe squint a little bit, and you will see that it's just a quadratic equation. So this is something that we are really quite familiar with and can solve. The fact that it's not just x, but rather y to the e to the x is a little complication that we can work around. So let me name it something else. Let's say that instead of e to the x, I'm going to call it y. Okay, and then replacing it, I can certainly see the structure, the quadratic structure of the equation much better. So for this one, there's a number of ways that you can solve a quadratic equation, and if you need practice with that, please take a look at earlier modules for solving equations, and in particular the quadratic types. One of the ways, of course, is to use quadratic formula, or to think of factors that will give me the necessary constants. So in this case, I can easily factor this out into y equals minus 2, y minus 2 and y minus 3, because negative 2 and negative 3 multiply to be 6 and add to be negative 5. And then once again, once I have things factored out, it means that either my y has to be 2 or my y has to be 3 in order for the entire product to be 0. Now recall that your y is actually e to the x. So I have e to the x is 2 or e to the x is 3. And now the problem here, of course, is I don't really know how to solve these equations yet. So it's the same issue as we've seen here. If the numbers are nice and we can reduce them to the same base, that's one thing. But if the numbers are not quite of the same integer structure, then we don't really know how to bring the power down in order to isolate it. Okay, so this question, we have to leave it as is for now and try to develop tools that will actually help us solve equations of this type, which is coming up on the next page. For now, though, just for one last example here, let's think about inequalities that involve exponential functions. So this is asking for which values of x will I have e to power negative x plus 2 greater than 0. So it appears that I have a negative power and something is asking when is this entire expression greater than 0. Now recall that anything to power of whatever number, so as long as you have a number here, raising it to no matter what power will never be able to produce a negative result. So that really means that immediately you get that for all values of x, will the e to the negative x plus 2 be positive? No matter what I plug in here, whether it's a positive x or a negative x, the outcome can never be negative because I'm simply raising something to that power. Logarithms and logarithmic functions, I feel, are like some of the most misunderstood tools out there, and that is because we have calculators and therefore don't always think about them from scratch. Here we will redevelop the understanding without using calculators as to what it actually means to be a logarithm. The logarithmic functions are actually simply inverses of exponential functions. So let's think about the process. Remember that inverse functions reverse the process. So what is the direct process, first of all? If you are to compute y equals 2 to the x, given the value of x, we simply raise 2 to that power, or we repeatedly multiply 2 by itself that many times. So raise 2 to power x, fairly straightforward. Logarithm, being the exact opposite of it, doesn't raise something to the power, it is the power. So logarithm base 2, we still say that 2 is the base here, so logarithm base 2 of x is simply the power to which we had to raise 2, or we have to raise 2, in this case 2, to get x. So exponential function actually raises the base to the given power. Logarithmic function is the power to which one has to raise 2 to get x. Okay, With this in mind and without a calculator, let's try to compute these values for the logarithm. Okay, so we start off with logarithm of base 2 of 8. So that's saying this is the power to which you had to raise 2 to get 8. So we can rewrite it as 2 to what power equals 8. The power that we need is the logarithm base 2 of 8. So of course 2 cubed is 8, which means that this logarithm is equal to 3. Okay, next one, logarithm base 3 of 1. So to which power did we have to raise 3 to get a 1? 3 to what power will give us a 1? Well, to get a 1 out of 3, we need to raise it to power 0, so that is the power that we need. Next up, 3 to which power is equal to 0? 3 to which power is equal to 0? And that, of course, does not exist. There is no power to which we can raise 3 to get a 0 ever. We've just discussed how a number raised to any power is strictly above 3. So this is one of the things that we will have to discuss in general when we're discussing logarithmic functions. Let's take a look at some things with fractions. So to which power do we have to raise 4 to get a 2? 4 to what power is equal to 2? Well, 4 needs to be raised to some fractional power in order to get 2 because it gets decreased. And in fact, we know that square root of 4 is 2, and square root corresponds to power 1/2, which means that the logarithm of base 4 of 2 is actually 1/2. Next up, what power did we have to raise 4 to get a quarter? So 4 to what power is equal to a quarter? Here I noticed that 4 simply traveled to the bottom, and the power that accomplishes that is -1. This logarithm actually got typed wrong, so this was logarithm of base 25 of 1/5. So to what power do I have to raise 25 to get 1/5? So notice that it's kind of similar to this question where the power first of all has to travel to the bottom, so we know right away that the answer is going to be negative, but also instead of 25 we received a 5. So we had to put it to the bottom and also take a square root of it. So the power that's required to do that will be -1/2. So notice that while I cannot have a 0 inside logarithm or anything negative, the logarithm can be negative itself. For more practice, let's take a look at this table. This will allow us to really develop an understanding of going between the exponential form to logarithmic form. So these are all equivalent expressions here. 2 to power cube or 2 to 3 equals 8 is the same as saying that logarithm base 2 of 8 is 3, because this is just saying that the power that we need to raise 2 into to get 8 is 3, right? 2 cubed is 8. So now, going through the rest of the table, we're going to fill out the exact same things across every row. I'm not going to fill out the entire table. I think that is a extremely useful exercise to do for yourself, but I'll do a couple of rows. So for example, I can start off on the next row here. 2 to which power will give me a quarter? So this is kind of similar to this here, kind of similar, right? So first of all, 2 had to travel to the bottom, which means that the power has to be negative, but then also 2 became a 4, which means that 2 got squared. So the power here has to be -2. Rewriting this in the logarithmic form means that the base that I had was, of course, 2, and the result that I got was a quarter. The power that was required to do that was -2. This last column contains logarithm used as an exponent expression. So in fact, instead of writing -2, because -2 is actually equal to this logarithmic expression, I'm just going to use that expression. So 2 to power log 2 of 1/4 is equal to 1/4. If I raise 2 to the power that I need to raise 2 to get a quarter, of course I get a quarter. Okay? This might seem a little artificial for the numbers that we're dealing with right now, but this property of logarithm being used as an exponent will become extremely useful when we're solving equations that involve exponents and logarithms. I'm going to skip the next row and I'm going to look at this one. So this expression right here says I'm raising 3 to the power of log 3 of 81. So I'm raising 3 to the power of logarithm that is required to raise 3 to get 81. So raising 3 to the required power to get 81, I'm going to get 81. Okay? Now, going back, so this does not actually specifically give me the value of the logarithm itself. So going back through, I can see that if I want to compute log 3 of 81, I'm actually going to have to think of this power as a number. So this is something that's easy to do on a calculator, but if the numbers are really nice, it's fairly easy to think of as an actual number if it's an integer. So what power do I have to raise 3 to get 81? And that power is 4, because 3 to power 4 is in fact 81. Okay. For negative powers, the situation is very similar, so I will leave you with this one. And I'm actually going to go through these last 3 rows. They do not have to have an exponential form. I am including them here just as a reminder about what it means to be negative. So be very careful about whether the negative is included outside of the square, inside, or in the power. These are 3 very different spots for the negative to occur, and therefore they will actually produce very different results. So if there are brackets, then of course the power affects everything in the bracket. Negative 3 times negative 3 is 9. Now, for the next one, let's take a look at here. There are no brackets, which means that we're assuming the most natural exponentiation. And if it makes you feel better, let me put the brackets around here. Okay, so 3 is being squared, and then the whole expression is being negated. So of course 3 squared is 9, minus in front of it will give me minus 9. The overall result here will be the power being negative 2, which means that 3 gets brought to the bottom and then squared. So the result here will be 1/9. Okay, I will leave it up to you to write all of these 3 expressions on logarithms, being very careful, but this is something you can also check on your calculator. So try to write down this expression as a logarithm and then actually maybe plug it into a calculator to just double check to compute to make sure that you got the right answer. Of course, take logarithms of any base, and the base is always stated in the underscript of the logarithm. So base 2, let's say, of 8. But one base that we use a lot is base e of whatever it is that you want to plug it in there. And because this is used so often, we actually have developed a shorthand notation for it. Instead of saying log of base e, we will say ln of x. This stands for natural logarithm, which is where we get the notation from. And this is one of the most useful logarithms. Every logarithmic rule that will work for a base e logarithm will also work for any other base. Taking a look at the sketching of the logarithmic functions, what we will use heavily is the fact that it is the inverse of an exponential, and we know how to draw inverses. So we will start with the graph of the original function, which is in this case e to the x. Now I know it's going to go through 1 as the y-intercept, and it's going to be a growing, increasing exponential function. In order for me to get the graph of the corresponding logarithm, it's the inverse of the exponential function, which means all I have to do is reflect the current graph in the y equals x line. So let me draw this line, y equals x. Let me make sure I label this graph as e to the x. And now I simply have to reflect this graph in this line to get the graph of the logarithm. Reflecting, you can think of it this way. You can think of this original graph as the one being drawn in wet ink or wet paint, and you are folding the page across this as a fold. Where will the graph leave the trace? So the point here will become a point here as you fold over, right? And the entire graph will transfer. The x-axis as the asymptote will become the y-axis as the asymptote, and it shouldn't take you very long to persuade yourself that the graph of the inverse function will look something like this. Okay, so one of the things that we could notice is, of course, the y-intercept becomes the x-intercept, and that's not terribly surprising because, look, e to power 0 is 1. So therefore, in order for the logarithm of base e of 1, I need to think of the power to which I have to raise e to get 1, and that, of course, is 0. And in fact, that will be true of any power, any base of a logarithm. The other thing that we can notice is, as I said before, here the x-axis was the asymptote, which makes the y-axis the asymptote here. The graph was increasing here. The graph is actually still increasing, but much, much slower. I will leave the second of the sketches up to you. It's the same type of idea, but now you have to work with e to the negative x as the actual graph. So with all of the properties of the logarithms in mind that we have witnessed on this page, let's summarize what we have seen. So for example, we have seen that logarithm of any base, let me call it b, of 1 is always 0, and that is simply because any b raised to power 0 will give me a 1. For a similar reason, if I have logarithm base b of b, that means that I have to think of what power did I have to raise b to get b, and that's of course a 1. Okay, so this is because b to power 1 is just b. And again, all of these will hold for natural logarithm as well. Another useful one is the fact that logarithm base b of b to some power a. So now let's think about this one. What power did I have to raise b to get b to power a? Well, clearly I had to raise it to power a. And then the last one is kind of the opposite of this one. B to power logarithm b of a. So here, logarithm b of a represents the power to which I had to raise b to get a, and now I'm actually raising b to that power. So I'm going to get a. The domain and the range of the logarithm, as we've witnessed before. So for the domain, the things that I can plug in the domain for the logarithmic function, so logarithm base b of x, the numbers that can go inside the logarithm have to be positive numbers and cannot be 0. We've seen that on the previous page. So the domain are all positive numbers, and the range, we have seen that before as well. What I can get as the answer can be positive numbers, can be negative numbers, can be 0. So the range is actually going to be all real numbers. Remember that in the case of the exponential functions, these guys were reversed. We could plug in any number, but what we would get as the output are only positive numbers. And that makes sense too, because the exponential and the logarithm are inverse functions. So the domain and range also change roles for those two functions. In terms of sketching the transformations, as before, the transformations will work the exact same way as we have witnessed before. Let's actually just have 4 plus logarithm here. So if the transformation is applied to the x directly, this will represent a horizontal shift. So in this case, it's a shift of 6 to the left. And if it's applied to the outside of the function, it is a shift of vertical kind. And in this case, it is 4 units up. So as before, I will start with the sketch of my base function, which in this case is going to be simply logarithm, natural logarithm of x. So I remember that it has the x-intercept at 1, it approaches the horizontal asymptote, the vertical asymptote of the y-axis, and it's a function that looks like this. And now I have to simply move this function 4 units up and 6 units to the left. Okay, so once again, I'm going to pick a point as some kind of special point that will be easier to move. So for example, this guy, I have to move it 4 units up and 6 units to the left. 1, 2, 3, 4, 5, 6. Okay, so in this case, I can also, let me just mark this as I've moved it 6 units from 1, which will make this -5. But I can also think of some other important features. So for example, the fact that the y-axis was a vertical asymptote which means that I can move it 6 units to the left, and it has to be a vertical asymptote of my new function. So at -6, I'm going to have a vertical asymptote for my logarithmic function. And the point that corresponds to this crossing is now traveled up here, so it's the point over here, okay? So my new graph is going to have to go through this point, approach this new line as the asymptote, and then continue growing. So this is my function f of x, okay? Once again, here I have an opportunity to solve for the y-intercept and the x-intercept. The y-intercept is going to be easier to get, so let's talk about that one for a second. I'm going to set x to be 0, so I'm going to get y is equal to 4 plus ln of 6. Now, this is not an expression that I can calculate in my head, but if you actually get the calculator out, you will notice that you can turn this into a decimal expression and therefore come up with the point where the graph crosses the x-axis, the y-axis. For the x-intercept, I need to set y to be 0, and so I'm going to get 4 plus natural logarithm of x plus 6 equals 0. And now I am faced with a little bit of a dilemma because I don't really know how to get this x from inside of the logarithm just yet. Okay, so we're going to spend a little while developing our understanding of how to solve logarithmic equations, going from the simpler ones to the more complicated ones. So let's start with a couple of simpler ones where we don't actually need any logarithmic properties. We simply need to remember the actual definition of a logarithm and be able to go from the logarithmic form to the exponential form. So remember that logarithm represents the power to which we have to raise a third to get x. So this expression right here says that in order for me to, the power to which I have to raise 1/3 to get x to is 9. So 1/3 to power 9 is actually equal to x. Well, this is great news because I don't even have to do anything anymore. This is already a number, so I can calculate this as a number. Taking a look at the second one, that's going to be a little more complicated. So here, it's the exact same logic, except for x appears in the base and not on the inside of the logarithm. But the logic stays the same. This logarithm represents the power to which I have to raise 1 minus x2 to get 16. So 1 minus x to power 2 has to be 16. Okay, these are equivalent forms. This is the logarithmic form. This is the exponential form. Okay, and now I am down to simply quadratic equation in x, so I can solve that. Opening up the brackets, or simply taking square roots of both sides, I have that 1 minus x has to be plus or minus 4, which gives me that x is either -3 or 5. Now remember that logarithms do have a domain, and in particular here x occurs in the base. And remember, from the very first definition of exponential functions, we've defined them so that the base has to always be greater than 0. So here, because I have a variable in the base, I need to make sure that whatever I get as the answer matches the fact that my definition necessitated the fact that the base has to be strictly positive. So if I plug in -3 into the base here, I'm going to get logarithm of base 4. Okay, maybe let me write this down. Logarithm base 4 of 16. And that of course is 2, because to what power do I have to raise 4 to get 16 is in fact 2. But if I plug in the 5 in, I'm going to get logarithm of base -4 of 16. We cannot have a negative in the base, which means that this solution is extraneous. Okay, so I'm going to have to disregard it, and altogether I have only one solution here. So in checking for extraneous solutions, we will add logarithms as the one of the types of equations where we actually have to go back and check through to make sure that our solutions make sense in the setup. Playing a little bit with, let's take a look maybe at these 3 examples next, of comparing but without using the calculator. okay? So here I have logarithm of base 5 of 100 versus logarithm base 6 of 100. So again, utilizing the exponential form here will be useful. So the logarithm here says this is the power to which I have to raise 5 to get 100 versus the logarithm base 6, which is the power to which I have to raise 6 to get 100. Which one of them will need to be larger? Well, I have to either be raising 5 to some power to get 100 or 6 to some power to get 100. So which power will be required to be bigger? Larger power is needed to get to 100 from the smaller number. So in this case, 5, logarithm base 5 of 100 will be bigger. Here, larger power will be required to get to the same result of 100. For the next one, logarithm base 10 of 99, logarithm base 9 of 82. So log base 10 of 99 means the power to which I have to raise 10 to get 99. Log base 9 of 82 is the power to which I have to raise 9 to get 82. Okay, well, these are some nice numbers. Notice that I know that 10 squared is 100, which means that whatever this logarithm is has to be slightly less than 2, because if this was 2, I would have gotten to 100. I'm at a smaller number, which means that this logarithm has to be less than 2. On the other hand, here, I know that 9 squared is 81, which means that to get to 82, I had to have a power that is bigger than 1. So here, I have something bigger than 1. Which one is larger? Well, this number is surely less than 1, and this number is surely bigger than 1, so of course this one will win. Okay, something very similar is going to go on here, but you got to be a little more careful, because once you introduce fractions, you start thinking of negative numbers. Okay, and negative numbers just require a little more detailed analysis in order to decide which one is larger and which one is smaller. So log base 4 of 118 means I'm raising 4 to some power to get 1 over 18. And here it's also the same base. So 4 to what power will produce 1 over 20? Well, I know that 4 to power negative 2 will give me 1/16. Let's try something more with a negative power. So for example, 4 to power negative 3 will give me 1/64. So notice that as I increase into the negative direction, so really I am decreasing in terms of x is getting smaller and smaller, but larger and larger positive, my denominators become larger and larger. Okay, so we're going to have to, as we move into the negative direction, our denominators increase, which means that to go from the denominator of 18 to the denominator of 20, these powers had to move further into the negatives. Further into the negatives means a physically smaller number, which means that this power here will produce a larger number or less negative of a number, right? So -2 is larger than -3. So this logarithm here will be larger than this logarithm here. Okay, and then finally here, the comparison again between the logarithm and the zero. So we can think, as opposed to the exponential functions, logarithms are allowed to be negative. So here we really have to think of it in terms of, for example, a graph. So if I start with the logarithm of x, it's the graph that looks like this, going through the point 0, 1. Then the transformation here, -2, means I'm moving the entire graph 2 units to the right, which will then mean that this point, for example, gets moved here. My entire asymptote gets moved 2 units to the right, and my graph would look like this. So this is the graph of ln of x minus 2. Now, the question is asking, where is this graph bigger than 0? Bigger than 0, so this is the y-coordinate now. Bigger than 0 means above the x-axis. Above the x-axis, of course, occurs on this portion of the graph or immediately after the new x-intercept. So for what values of x is it positive? For the values of x that are greater than 3. Okay, so this is another major difference between logarithms and exponential functions, is logarithms are in fact able to take on negative values, so then inequalities with them need slightly more careful consideration. Because exponential and logarithmic functions are inverses of each other, every exponential law has an analogous logarithmic law for it. Let's start off with the two cancellation laws that we've already witnessed, but these guys are stated in terms of natural logarithm and the base e of the exponential function here, right? So this is saying that if the two functions are applied immediately after one another, they cancel each other's action and you simply get x back. So e to power of logarithm of x is just x, and the other way around works too. So if I first apply the exponential function and then the logarithm, then I simply get the x back. Again, recalling all of the exponential laws, here are the corresponding logarithmic laws. The logarithm of a product is a sum of logarithms. If you have a logarithm of a number to some power, that power can come down to be in front of the logarithm. And then the quotient, the logarithm of a quotient is a difference of logarithms. I would like to caution you against an incorrect use of these logarithmic laws, and in particular, there is no law of logarithms that allows you to break up the logarithm of a sum. We can break up a logarithm of a product or a logarithm of a quotient, but nothing will allow us to break up a logarithm of a sum. This is not ln x plus ln y. This is not ln x times ln y. In fact, this is not easy to simplify, and you cannot simply do that. The other thing I'd like to warn you about here is the fact that in order to use this law, this power has to be the power of everything on the inside. So for example, if I have something like logarithm of 3x to power 5, this 5 cannot come down here because this 5 is only the power on x and not on 3. So this is not equal to 5 ln 3x, okay? The only way to simplify this, so this is incorrect, okay? It doesn't work like that. The only way to simplify this is to first apply this rule, because before power 5, this is a product of two things. So we have to first separate that as a product, and then once you have logarithm of x to the 5th, then you can apply this rule of bringing the power down. Now, all of these rules and laws actually allow us to solve exponential and logarithmic equations quite efficiently. So for example, let's take a look at this. E to power 3x is equal to 5. Now, the fact that I have these cancellation laws, that comes from the fact that the exponential and logarithmic functions are inverses of each other, is what allows me to extract x's from the power and bring them down using logarithms. So what I'm going to do is take logarithm, natural logarithm, of both sides. Okay, so if the two sides are equal, then the logs of both sides will also be equal. Then, as per cancellation law, if I apply logarithm and exponential function to, in this case, 3x back to back, then they will cancel each other out, and I simply get the power back. Okay, so in this case, I have that 3x is equal to ln 5. The other way to think about this is to notice that this is in fact a power of everything on the inside, so it can come down into the front. So I have 3x times ln e, and ln e is simply 1. Okay, once I have this expression, ln 5 is just a number that you can calculate using your calculator or any other program. So here, to simply isolate x, I'm going to divide both sides by 3. You can leave the answer like this, or you can turn it into a decimal expression. Just be careful that if you are using an online homework in your calculus course, the more decimal places you include for this one, the better. Some homework systems require better precision than others, but all of them will be able to take the exact answer like this one. Taking a look at this is kind of like the exact opposite of the equation above, where the 3x resides inside of the logarithm. So in order for me to extract it from the inside of a logarithm, I'm going to raise both sides to the power of e. And then again, as per the cancellation laws, if I have e and logarithm applied back to something, I simply get that argument back. So 3x is equal to e to the 5. Recall that e is simply a number, so e to the 5 can also be calculated as a number. So here, in order to solve for x, I will also just divide both sides by 3. Again, you can leave this as the exact expression as is, or you can expand it out as a number. In terms of logarithmic equations, there are a number of approaches to them, and I will show you a couple across the two examples that we have here. So first of all, here's where we're really going to start using logarithmic rules. On the left-hand side, I have two different logarithms. Here, the reason that I was able to raise everything to power e and everything canceled out so nicely and so quickly is because I had a single logarithm. So while you can raise everything to power e right away, you will then face more simplifying steps than you have to. So the more efficient way to go is to first of all combine these two logarithms together. So I noticed that the sum of two logarithms is a logarithm of a product. So this can be put together into one single logarithm that becomes logarithm of x times x minus 5. Once I have one single logarithm, I can do something similar to what I've done here and raise e to the power of both sides. Now, once again, when e and logarithm are applied back to back, according to the cancellation laws, I will simply get what's inside the log. And on the right-hand side, I have e to power 1, which is just e. Okay? Opening up the brackets here, let me move everything to one side. So I'm going to have x squared minus 5x minus e equals to 0. Remember that e is just a number. It's not a number that's easy to write out or that you can write out exactly, which is why we have this notation for it, but it's just a number. So really, my only variable here is x, and it appears to power 2 and then to power 1. So this is simply a quadratic equation. And because obviously I cannot think of easy ways to factor it out, we will have to apply quadratic formula here. Now, I'm not going to go through the application of quadratic formula, but please feel free to finish this off. One more step that I'm going to mention that you have to do at the end, because here you have logarithms of two different values. You have to make sure that whatever goes inside, much like with a square root, is in fact positive. So whenever you apply the quadratic formula and get roots, as the last step, you must check for extraneous roots. By plugging every root that you find or every solution that you find back into their original equation and making sure that you're not breaking any domain restrictions. For this last question here, I'm going to do it in two different ways just to showcase two different approaches to this. So one of them, I can do something very similar to what I've done before, and first step in my solution, I would combine the two logarithms together. So I will get ln of x times x squared, because the sum of logarithms is a logarithm of a product, equals to 5, which means that ln of x cubed is 5. And then I can again raise everything to power e, which will then give me x cubed on the left, because the exponential and logarithmic function will cancel each other's actions. And on the right, I'm going to have e to power 5, which will then give me that x is a cube root of e to the 5th. Okay, and again, I can compute that as a number, but I'm just going to leave it here as is. Another way to have proceeded would have been to apply this law of bringing powers down first. Okay, so here I notice that I have x squared inside the logarithm, so I'm just going to bring the 2 down first of all. So I'm going to start with ln x plus, then it becomes 2 times ln x equals 5. Okay, and so now I can have similar terms on the left here. I have logarithm plus 2 of the logarithms. So it's like apple plus 2 more apples is 3 apples in total. So I have 3 logarithms of x equals 5. I can of course now solve this expression for the ln. So it's going to be 5/3. And then in order for me to extract the x from inside the logarithm, just like I did here, I'm going to raise both sides to power e. The exponential and logarithm will cancel each other out on the left, and on the right I'm going to have e to power 5/3. Now, of course, notice that these are the exact same expressions because this is just the square or the cube root written out as a fractional power. So my answers are the same for both cases. For both cases, I do have to plug the answers back in to make sure that I'm satisfying the domain restrictions for the logarithm and the fact that whatever I put inside the logarithm has to be positive, which in this case, this root is. So this is then going to be my solution to this equation. One more thing that I'm going to mention in this video before I send you off to practice is the fact that logarithm is an operator, just like, for example, a square root. So just like you cannot have a square root of nothing, you cannot have a logarithm of nothing. So ln by itself is not a meaningful expression. It always has to be followed by a number that you're actually taking the logarithm of, or by some kind of variables, okay? So if you have an empty logarithm, it's like having an empty square root. That's just not a thing, okay? So please make sure that you do not include things like this in your calculations. Take a look at Workbook Assignment Module 5a. It has a lot of examples that really allow you to practice with logarithms and exponentials and get your hands on the graphs and the various ways to solve equations, including them, that will be essential in calculus.